When I hear faster than light without warping space, my skeptic brain lights up. But curiosity wins. So let's unpack Rodney Kawecki's quanta physics theory, his reverse vacuum space field drive. The headline idea, space itself can be repulsive, and that repulsion, like the expansion of the universe, could push a spacecraft faster than light without bending space-time. Instead of an Alcubierre bubble or classic warp, the drive would ride a repulsive vacuum. Tap into the same equations that govern the Hubble expansion and use them as propulsion. In Kawecki's framing, the vacuum has a built-in push. If the universe can expand, maybe a craft can expand its travel load with it, gaining speed beyond light. He builds this into a bigger update he calls the quanta physics theory. One piece, a twist on ERMC2, proposing ERMV3, linking energy to velocity and a kind of quantum step frequency per second. Another piece, the popcorn universe. Imagine the Big Bang creating a central bubble where matter popped outward, like kernels bursting and flying away from a center. He also argues light speed isn't the ultimate limit, because the space vacuum environment can change and be engineered. And for the record, no time travel here. In this view, time is just how we measure motion, not a dimension you can ride. Okay, how does this sit with established physics? Standard cosmology says the universe's expansion, often linked to dark energy, stretches space. But locally, gravity and forces keep systems bound. You can't normally hitch a ride on cosmic expansion to zip across town, much less between stars. Relativity says nothing outruns light and vacuum locally. Thousands of experiments, particle accelerators GPS, agree. So if this reverse vacuum drive is real, what would convince me? A clear, consistent set of equations, reducing to known physics in the right limits, and making new, precise predictions. A lab-scale effect showing controllable directional thrust from a vacuum interaction that can't be explained by stray heating ions vibrations. Think micro-Newton tests with null controls. Distinct relativistic signatures. If you claim FTL without time dilation, then show measurable discrepancies, clock rate spectral shifts. Cosmological tests. If there's a popcorn center, we should see a preferred direction in the cosmic microwave background. Galaxy flows. Could the vacuum be engineered? We do alter vacuum states in cavities. The Casimir effect is a tiny force from quantum fields. But scaling that to starship thrust is a leap that needs hard data. I'm skeptical because the bar is high. Yet I'm curious, because if even a small part is testable, we can ask better questions. For example, can a tuned electromagnetic cavity measurably modify radiation pressure, zero-point energy density? Can we design blinded, multi-lab experiments with pre-registered analysis to rule out artifacts? Extraordinary claims don't die in debate. They live or fall in experiments. If a reverse vacuum drive is possible, it will leave footprints we can measure, reliably, repeatably, and in public. Until then, treat these ideas as provocative hypotheses, fuel for thought, not flights. And if you're working on bold physics, show your math, make risky predictions, and invite everyone to try and break them. That's how impossible becomes possible, or impossible for good reasons.